All right, so looking at this problem from the homework last night to start off before we get into some new topics here, we're talking about a function f is blank on an open interval I if for any choice of x1 and x2 and I, with x1 being smaller than x2, right, then the value, the y value that relates to x1 is going to be smaller than the y value that relates to x2. So essentially what we're saying here is for any two values of x on this interval, right, the smaller x value is always going to give a smaller y value compared to the larger x value, meaning the function is increasing, right? Function has to be increasing for that to be true, so the vocab word we're looking for there is increasing. Okay, that's just a very formal way of defining what it means for a function to be increasing on an open interval. All right, other questions from the homework? All right, number 27 from the homework. So, number 27 in your text, you're asked 4 different questions. First of all, what are the intercepts, both x and y? That's part A. So for part A, the intercepts, the y-intercept, or we know if it's a function, there can only be one y-intercept, and that occurs at 0, 1/2, right? And the x-intercepts of this function occur at 1/3, 0, and 5/2 is 0. Whoops, so those are both part A right there. The domain and the range. What is the domain, assuming, and we don't see, it's important to note we don't see arrows, right? It's important to note that we don't see arrows right here, right? So this does not continue on to the left, and this does not continue on to the right. So knowing that it stops here and it stops there, what would my domain be?
Close -3, and then close 3. Or 3 close.
Yep. So -3 to 3 be the domain. What's my range going to be? All the values of y that we reach.
Close -1, and then 2 close.
Yep, to 2. So that's the domain and the range of the function. For part C, we are asked to find the intervals over which it is increasing, decreasing, or constant. Let's start with the intervals over which it is increasing. Where is it increasing?
2 to 3.
2 to 3, yep. And we're going to use open intervals because when it's neither increasing or decreasing, or when it changes from increasing to decreasing, or from constant to increasing, we're going to assume that at that point it's neither increasing or decreasing. So we're going to use open intervals for these ones. So that means it's going to be 2 to 3. Decreasing on the intervals, what?
-1 to 1.
Yep. And constant on which intervals? Or what interval? Or both?
-3 to -1, and then 1 to 2.
Yeah. So that's part C, and lastly part D. Is it even, odd, or neither? Does it look like it has any type of symmetry? No, so it is neither. All right, so that's number 27 from your homework. A, B, C, and D all answered. So today we're going to start off by talking about the greatest integer function, which is notated either like this or this. So this function applies an operation to x, which is the definition of the greatest integer function is that f of x gives the greatest integer, which is where this name comes from, that is less than or equal to x. All right. So let's try and if that's what the greatest integer function is, let's just try and take some values of this. So for instance, int of 2.3. What is the largest integer that is less than or equal to 2.3? What about int, whoops. What about int negative 5.8, if I'm making a negative number? The largest integer that is less than or equal to that. Negative 6, right? We could go down. What about int of 4? That's just 4, right? So yeah, if it is actually a whole number, it doesn't actually change it. All right, so this is strange. It takes whatever number we have and it rounds it down essentially to the greatest integer value, right? To the greatest integer value that's less than or equal to whatever the number is. And so it's an interesting function because it's what's going to be called, and we'll talk about this in a second, a discontinuous function, right? And so what I'm going to do here is I'm going to go ahead and graph the function for us on the next page. All right, so on the previous page we were talking about the greatest integer function. Let's go ahead and see what that would give us for a graph. If every single x value, we take every single x value on the domain and we round it down to the biggest integer value that's less than that x value. So I'm going to go ahead and type this in here. Y equals, and this is going to be in our functions here, miscellaneous. And often it can also be called the floor function. Right? And so if we go ahead and look at this here, it looks like sort of a bunch of steps, right? Which makes sense because if I take, for instance, in this area right here, if I take any x value in here, the y value I'm going to get is going to be 1 less than that. So like, for instance, x is 1.5 right here, and instead of y being 1.5, we round it down to 1, right? Like if we're right at 1, that stays 1, right? And int 1 is equal to 1, int 2 is equal to 2, int 3 is equal to 3. Unfortunately, this graphing calculator here doesn't. I guess I can't really go and do anything with this, unfortunately. Let's see here if I can. There we go. Unfortunately, this graphing calculator right here doesn't actually show like open dots and closed dots depending on where the function's defined for. So for instance, what's going to be going on right here, imagine that right here, would this be a closed dot? Let's start at the bottom here. What is int 0? 0. So int 0 is 0, so that should be a closed dot, right? That's defined as 0 right there. And then any value that's greater than 0 but still less than 1 is going to have a 0 value for y, right? But what's int 1? So this dot right here should really be open, right? And this should be closed. And over here, this is open and this is closed. Open, closed. So see where we should have open, open, open. All of the right ends of these steps should be open, and all the left ends should be closed. Right, and and probably the most interesting part of this function is that it is broken, right? There are big gaps in the lines of the function, which is something that we're not necessarily that familiar with. And this is because the function is discontinuous. So, that's a new idea, the idea of a discontinuous function. Ernie is a function with breaks or gaps in its graph, right? And a continuous function is, of course, the opposite. A function with no breaks or gaps in its graph. All right, so that's a continuous function versus a discontinuous function. And the int function is an example of a function that is a discontinuous function. Right? And the int function is also what we call a type of step function. So, because it looks like a bunch of steps, sort of an obvious name. And it is discontinuous, as we said. Okay. So that's the int function right there. And you can also, of course, graph it in your TI-84 graphing calculator. Just for reference, if you wanted to graph this in your TI-84 graphing calculator, you would go into y equals and you would hit the command. If you go ahead and hit, go into your y equals in your graphing calculator and hit math, right, and then scroll over to the NUM menu, int is number 5. Int, parentheses, and that is the greatest integer function, which is our step function we just talked about. So you can go ahead and graph that on your graphing calculator. You have to just put an x, of course, so you do int x. And hit graph, and you should get pretty much the same, well, the exact same graph that we saw in the previous page on Desmos. Now, the major focus of today is going to be the concept of a piecewise function. Piecewise function, okay. So a piecewise function is a function that has different definitions over different domains. Or over different parts of its domain. Right, and you're actually already somewhat familiar with a piecewise function. And the one that you're familiar with is the absolute value function, which is in a sense a piecewise function. Now you have to remember that the absolute value function looks like so. Right, this is the function. Y is equal to absolute value of x. Right? Whoops, that is not what it looks like. Let's just go ahead and fix that. So it sort of looks like that. And so when x is greater than 0, it sort of behaves just like the function y equals x, right? And when x is less than 0, it sort of behaves like the function y is equal to negative x, right? It has the slope of -1 instead of +1. And so what we could do is we could define this in two different parts here. We could say that instead of y is just equal to absolute value of x, right, that's equal to what we're going to use is we're going to put a big bracket here, right, and say that, well, if it's equal to x when x is greater than or equal to 0, let's say, then it's equal to negative x when x is less than 0. So we've essentially taken this function, the absolute value function, and defined it in terms of two separate intervals, right? When x is positive or 0, it behaves just like the function y is equal to x, right? This looks just like the function y equals x, slope of 1, goes to the origin, all that stuff. But when x is less than 0, it behaves just like the function negative x, right? Goes through the origin, but has a slope of -1, right? And so this is an example of a piecewise function. We don't often break the absolute value function apart this explicitly. We just sort of know that's what this means. But this is really what the absolute value function is. Depending on where your value of x lies, whether it's to the right of the x-axis or to the right of the y-axis or the left of the x-axis, is going to depend how we apply this definition. And in a sense, the step function is also sort of a piecewise function because depending on, we see that it's defined differently for different x's in its domain. You know, if it's, for instance, so for the greatest integer function, is sort of like a step function in a way. Right, so for instance, and I could keep going with this, but let's say that if f of x is my greatest integer function, I could almost define that in a piecewise way, right? Except I'd have to keep going up here, and we'd say that it's equal to I guess we'll start with 0. It's equal to 0 if x is between, right? It should be less than. If x is between 0 and 1, it's equal to 1. If x is between 1 and 2, but less than 2, it's equal to 2 when x is between 2 and 3, but less than 3. And then this keeps going on, of course, right? So in a sense, the int function is also a piecewise function in a way. And the int function, we also, by the way, just as a side note, it's often also called the floor function. Right, so floor x is another common way of notating that in addition to the sort of bracket like that. So those are two other ways that is referred to. In most cases with piecewise functions, on the other hand, we're usually given the definition. So for instance, I might have the function f of x equals let's say it's equal to 2x plus 5 when x is less than 0 but greater than or equal to -3. Maybe it's equal to -3 if x is equal to 0. And then maybe it's equal to -5x when x is greater than 0. So this is another example of a piecewise function. And so, like we said, it has different definitions. This is the definition when x is between -3 and 0, but less than 0. When x is equal to 0, it's equal to -3. And when x is greater than 0, it's equal to -5x. So let's go ahead here and see how we're going to graph this. Because what you're going to be doing a lot of is graphing piecewise functions. Or going in reverse and taking the graph of a piecewise function and writing the actual formula for the function. So let's go ahead and we'll start at -3 to 0. Right? So the first interval we're going to tackle here is between -3 and 0. So this interval right here, it's defined as 2x plus 5. Now, when x is -3, what point does it go through? What's 2 times -3? 2 times -3 plus 5. Well, that's -6 plus 5 is -1, right? So when we're at -3, it should be equal to -1. And this is, by the way, this is less than or greater than or equal to. So at -3, it equals this, right? It's not defined right there. So should we put a closed dot or an open dot then? Closed dot, yes. So closed dot right there, right? I want to go red. And then when we're on the other end of the interval, at 0, what is this equal to? 5, yes, so 1, 2, 3. Wow, I really didn't scale this very intelligently. All right, so when x is equal to 0, f of x is going to be equal to 5, which is up there. Which is up there, right? And so what type of function is 2x plus 5? Linear. So how should I connect those two dots? Ooh, should this have been an open dot or a closed dot? It should be open. Why should it be open? when it's less than 0, it's equal to this, right? If it was less than or equal to 0, then that would be the definition right there. But at 0, it's defined to be -3, not whatever it is here, which is 5. So we should put an open dot around 5, and then they need to be connected with a nice straight line, like you said, because it's a linear function. Right? And at -3, x is equal to 0, right? So, sorry, at 0, I should say, y is equal to -3. So we got to go ahead and go down 1, 2, 3. And the actual definition is down here, so that's going to be a closed dot, right? And then when x is equal to -5x, sorry, when x is greater than 0, it's equal to -5x. So that's going to be 0. It's going to start at 0, because -5 times 0 is 0. And that's going to be an open or closed dot at 0? Open, because it's not actually, it's defined to be this at 0, but it does start at this when it's going to the right of 0. So we do have to have the dot there. It just needs to be open. And then it's a nice straight line, and it has a slope of what? -5. So it's going to look pretty steep and just go straight down from there, right? So it's going to sort of look like that. So that's what our function would look like there. Let me ask you this. What is the domain of this function? What are all the values of x that we get to? What do you think, guys? You think it's closed? Yep, sorry, that's an open one. Closed, yep, -3.
And then open 0.
Yeah, I was going to say it's defined for 0, right? So it really, there's no break as far as x is concerned, right? Even though it's a discontinuous function.
Yes, you go.
Does it just keep going forever?
Infinity, yeah. So infinity.
Yep. What's the range going to be?
Open 5.
Yeah, because it didn't quite get to 5, but yeah. Well, is 5 the top or bottom of the range? Yeah, so that's going to be on the other side. Oh my gosh, start recording. Okay, so the range here, it goes all the way up to 5, but doesn't quite get to 5, and then goes all the way down here to -infinity. So it's going to go from -infinity up to 5, but not including 5, so that should be open. Infinity is always open, right? So there's the range of the function. There's the domain. We sort of already mentioned the fact that this function has some pretty big breaks in it, right? There's pretty big gaps. It's not connected, and so we're going to call this a discontinuous function. There's an example of just a regular old piecewise function. If you're given the formula of the function, you want to be able to graph a particular function. But we also want to go in the other direction. So let's now go ahead and we'll take a look at the graph of a piecewise function and see if we can't come up with a formula for that function. So sometimes we are given the graph of a piecewise function. We want to actually be able to write out the formula for that function. So here's an example. We have this piecewise function right here. We can see that it's defined from -1 all the way out to positive infinity here. Right, but it's not really defined at all over here. There's just no definition to it. Sometimes it'll just have big gaps in its domain that aren't actually filled in. So let's go ahead here and come up with a formula for this particular function. But what I'd like to do first is just identify the domains over which the function is going to be defined. So what's the first interval over which this function is going to be defined, or have a specific definition? What do we think, guys? What's the first, going from left to right. Let's start in the left and work to our right. What's the first domain we're going to have here? First. -1 to 0, and then 0 to
2. Or beyond.
Yeah, it keeps going, yeah. So we have two separate intervals here we have to define it on. So between -1, whoops. And we always use inequality notation with these ones. That's going to be less than or equal to, so x is going to be greater than or equal to -1. And then it's going to be, it's a closed dot at 2, so it's going to include x equals 2, right? And now we get in a second we'll figure out what that function is. And then the other one, it's going to be x is what? Greater than 0. Oops, and I screwed the other one up, didn't I? That should be 0 there. Should be -1 to 0. It's going to be defined as this line right here, and 0 to infinity, it's going to be defined as this line. So, let's start with the first one first here. This one right here. How do we find the equation of that line that passes through those 2 points? Because that's going to be the definition for that interval, right? If we have a line that passes through 2 points, and one of those points, thankfully, is the y-intercept, right? Then do we have to use point slope form? No. What's the slope, first of all? It's going to be, what? 2 minus 0 over 0 plus 1. Slope of 2. And what's the y-intercept?
2.
So the line is y equals 2x plus 2. So that's going to be the definition over the interval, right? And now what's the slope of this one right here? 1, yep. We can just look at the, we see that it goes up 1, right, for every one that it goes over, so that one's easy enough. And so the equation is going to be x, and what's the y-intercept? So just x, right? So there we go. Relatively easy to write the formula for a piecewise function if they're just linear functions. Obviously, this process gets a lot more difficult if they're not linear functions, but all the ones that you're going to see in the homework tonight will be linear functions, so it's just a matter of going ahead and writing those definitions for that by finding the equations of the lines after you've identified the domains over which they need to be defined. So, piecewise functions are important because they have a lot of sort of real-life applications, and so we're going to go ahead now and look at some word problems that involve piecewise functions. So, piecewise functions actually come up a lot in billing problems when some company is billing you for hours or minutes or kilowatt hours or whatever it happens to be, because your rate sort of depends on how much you use. You know, you go up and do different brackets sometimes. Taxes are also an example of piecewise functions. You get charged a different tax rate depending on what tax bracket you're in, right? So that would be a piecewise function. Depending on how much money you make, you get charged a different amount or a different percentage. And so there's a different function that they use to calculate your taxes depending upon what bracket you fall in. But in any case, this example right here, we have a situation where we're talking about electricity, right? So in May 2006, this company charged the customer $7.58 plus this per kilowatt hour fee for the first 400 kilowatt hours, and $6 and 6.208 cents per kilowatt hour for every hour over the 400 kilowatt hours they use in the month. So depending on how much they use, it's going to affect what the formula is for calculating your charge. So for part A, just go ahead. We won't worry about actually writing up a function. We're just going to calculate it here. So what is the charge for using 300 kilowatt hours in a month? How am I going to calculate that using the formula they've given me? What do I have to start off with always, no matter what? Yeah, there's a flat charge of $7.58 plus, how much am I charged for that 300 kilowatt hours I'm used? 8.275 cents times 300 kilowatt hours. What do I have to be careful about here? That I'm actually sort of made a mistake already. Yeah, they have to be in the same unit. So I gotta, if this is in cents, then this also needs to be in cents. So that's how many cents? 758 cents, right? And if we go ahead and plug that into our trusty calculator, we'll end up getting 3,240.5 cents, which is roughly how many? That's like $32.40, let's say. Right? And for part B, what is the charge for 700 kilowatt hours? Well, how am I going to calculate that? I have to start with my 758. Then I have to add 8.275 for the first 400, right? But then they charge you a lower rate for every kilowatt hour over 400 hours per month. So then your charge for the last, how many hours is that? If we're using 700 hours total? 300, so you're going to be charged as 6.208 times 300. right? And that is going to be approximately equal to, and so that ends up being about $59.30. And so now the last thing we want to do is let's go ahead and say I'm given any number of kilowatt hours X, and I want to have a function that will spit out, right, whatever the bill ends up being. All right, so let's go ahead and write a function for that. All right, so if we want to go now and for part C here, write an actual function, which we'll call C of X. Right, this is going to be a piecewise function, and of course, there's two different functions that are going to be used to calculate the charge depending on how many kilowatt hours you use. And so I should probably give a lot of space for this. What are those two intervals that we're going to be concerned with here? Between 0 and how many kilowatt hours a month is the first one going to be? 400. Yep, so between 0 and 400. That's going to be less than or equal to 400, right? Because if it's exactly 400, I still just use this one formula. But then if it's greater than 400, then I have to use a different formula, right? So what formula am I going to use if it's between 0 and 400? Let's do it all in cents here. I start off with my base costs, $7.58, or sorry, which is 758 cents, plus what? What do I have to add to that for the first 400?
8.275 times X.
Yep. And now all I have to do now is I have to do 758, and this is going to be, I'm going to end up going over here, plus 8.275 times what? Times the whole 400, right? Yeah. Plus, this is the tricky part, 6.2, I'm not going to fit this otherwise, plus 6.208 times what? X minus 400, right? All the hours over 400, right? So I have to take the number of hours, subtract 400, and those number of hours over 400 get charged at this rate right here. And so you could simplify this, of course, by adding 758 plus 8.275 times 400. You could also distribute the 6.208 here. And if you did all that, if you did a full simplification of this, you would get, if you go ahead and simplify that formula, you'll get 6.208x plus 1584.8 if x is greater than 400. Okay, so using what you know from the previous example, why don't you guys go ahead and take a crack at this word problem, and then we'll take a look at it. All right, so we have the car rental situation here. An economy car costs $95 per week. Extra days cost $24 per day until the rate exceeds the weekly rate, in which case the weekly rate applies. Also, any part of the day used counts as a full day. So half a day, still a full day. 3/4 of a day, like 1/4 of a day, still a full day. And they only want you to consider if you rented for between 7 and 14 days. So between 1 and 7 days, they're not having you worry about that. So let's go ahead and try and write a function for this. So really, we're going to have two domains here, right? Because the most you're going to pay is to rent it for 2 weeks if we're only between 7 and 14 days here. 14 days, you'll pay for 2 weeks. 7 days, if you don't go over 7 days, you'd pay for just 1 week, right? And in between, that's when it gets interesting, right? So, although if you rented it for exactly 7 days, how much is it going to cost?
95.
So actually, it's going to be. I lied. It's going to be 3 intervals. So it's going to if it's exactly If you rent it for exactly 7 days, then it's going to be $95, right? If you rent for between 7. If it's slightly more than 7, you automatically pay for another day then, right? Between 7 and Well, then the question is, when do we get to the point where we're actually paying, when would we get to the point where we're actually paying more than the weekly rate? When is 24 times X? How many days do we have to add before we get to the weekly wage? Well, 24 and 24 is 48, plus 24 is 72, plus 24 is 96. So after 4 days, you're actually, at the end of the third day, once you're paying for that fourth day, you're just going to pay the weekly rate, because if you paid for 4 days, that would be more than the weekly rate, right? So the way that we're going to do this is, I'm going to write out the formula first. For those days, you are going to start off with your $95, right? Let's say before we get to that point, actually. $95 plus, right? Plus the daily rate, 24, times, and this is the tricky part, if we have to pay for the full day, right? Essentially, we're taking the number that we've gone over 7, and we're rounding it up to the largest number, right?
24 times x minus 7.
Well, it's x minus 7, but we pay a full day price, right? Like if we use it for 0.5 a day, we still pay $24. We don't pay $12, right? So we have to take whatever that number of days over 7 is, we have to round it up to the next highest integer value, right? So we actually have to round it up. This is the opposite of the int function, actually. And so it's going to be 24 times x, times, and I think it's just going to be, we'll just call it ceiling. So 24 times ceiling, because we don't want to round down like the int function, which we also call the floor function. Cancel. Go away. Ceiling. Oh boy, eventually we'll get this. Of, like you said, x minus 7, right? And that's for x less than or greater than 7, but less than or equal to, but less than what? Less than or equal to 10, yes. Anything over 10, and then you're automatically paying the second weekly rate, right? And so let's say it's 11 days. Right, that would be 4 days more, and that would, if we paid the daily rate, it'd be 96, right? But we're not paying the daily rate, we're paying the weekly rate, and so from that point forward, we're just paying for 2 weeks, right? If you've gone over 3 days at all, if it's 3.2 days, 3.4 days, you're automatically paying for the full week at that point, because it's actually less than paying the day rate. And so what's the price going to be at that point?
190.
Just going to be 190, yeah. 95 times 2. Whoops, so between 10 and 14. Right? I already... So yesterday we talked about the idea of finding a local min or local max of a function, and that was where the function, a local maximum occurs when the function goes from increasing to decreasing, right? Function goes from increasing to decreasing, we have a local max. Function goes from decreasing to increasing, we have a local min. And we can locate those spots if they're not told to us, but we just have the formula for the function in this case. We can locate those by using our calculator functions. So what we're going to do is we're going to go ahead here and to answer the first question, which is after how many hours will the concentration be the highest? Right? So when is C going to be the largest possible value it can be? Let's go ahead and graph this function on our calculator and use our min-max functions to answer the question A. All right, so if we go ahead and we graph that function, we get a function that looks like this, right? And you can use your calculator to just use the use the max function. where using the max function, of course, you'll go and you'll put it just to the left and hit enter, just to the right and hit enter when they want to write bound, and then when you hear guess, just click it for a third time. It'll tell you what that maximum value is. In my calculator right here, it's a little bit easier. All I have to do is just go ahead and click on the point. And did you guys get 2.16?
Yeah.
So after 2.16 hours, the concentration will be the highest we see. Whoops. For the second part here, we want to figure out when is it below 0.5. So when is it below, the way we can think of this is, when is it below the line y equals 0.5, right? That's really what we're asking. So if we go ahead and graph that, we can see anywhere it's below that is where that would be. So if we go over here and we find the intersection point, the second time there's an intersection point, so we want to wait until after it goes back down below. We find that second intersection point is 4.465 hours. So she should wait at least 4.465 hours before she starts breastfeeding, because that's when, after that point, it'll have gone below the amount that is recommended, right? So we're going to put, and that's going to be 4.465 hours. And on your TI-84 calculator, you're just going to use to find that that's 4.465, that second intersection point, you're first going to graph y equals 0.5. And then you'll go ahead and use the second calc intersect button, or function, right? That which is in the same menu as the 0 one. And you're going to ask for, it's going to say curve 1, curve 2, select curve 1, hit enter, select the second curve, hit enter again, and then just scroll somewhere near the intersection point and hit enter a third time, and that should give you 4.465 as the intersection point. That's how long they should wait. All right, so that she's not breastfeeding when it's more than it should be. All right, so that's how we can use the idea of min and max to solve certain types of word problems like this. All right, so the homework for tomorrow will be the following. So that's your homework for tonight. Those are both the same handouts you already have. I did send out a new copy of those just in case someone lost them. But it's the same handout that I handed out yesterday, and hopefully by tomorrow, or if nothing else, by next week, I will have the new copy of the book, and I will just start assigning stuff out of the book as opposed to coming up with handouts every time. All right, have a good one.